All right, so today we are going to implement ChaCha20 in nMigen. So before doing that, let's just have a look at what it is and how it works. So it's a stream cipher. And it looks like this. So it's based around this 4x4 matrix of 32-bit words, which is our state. It's prepared with a constant like this, expand 32 byte k in bytes, like this. And then you fit it with your key and a position and a nonce. And then it will go through this operation 20 times because it's ChaCha20. And then finally you get something that you should add with the initial state for some reason. So here's the full implementation in C. The fun thing is that this is pretty easy to understand what's going on. Like, I cannot really reason why it is like it is, but it is like this and it works. So that's kind of nice. So the idea is to implement this in nMigen to be run on FPGAs. I've already done some homework. I have an implementation that works. But I hope that we can do some improvement on that and also set up some benchmarking framework and build basically an IP library, if you want, where we can add future other crypto implementations and benchmark them and reuse them and so on. Yeah. Okay, so I guess we can start with setting up a project. So, like all projects, we need a name. Thanks for the follow, and hi. Let me just fix my setup here. I hid the chat for some reason. Here, yeah, it's back again, I think. All right. Yeah, so I did some coding before. Oh yeah, here you get double chat. So because I'm really bad at focusing, like I can't really look at two things at the same time, I tend to keep the chat window on my main window when I'm coding. But yeah, anyway, let's see if I can do like this when I'm coding. Yeah. All right, cool. So yeah. I made this implementation a few days ago, where we basically implement the algorithm as simple as possible, I suppose. So there is a state machine where we go through, where we load the initial state based on the user's key, like the magic constant, the user's key, the counter, and then a nonce. And then we move on to the next state. We perform the rotation, which is defined as follows. So basically, these are just temporary signals, like wires in a Verilog. And then I have this comb logic where I generate the logic of the algorithm. So basically this picture, but with code, it's basically the same thing. Then here I'm storing the output in as a synchronous statement, so it will be registered, so it will be applied in the next clock cycle. And then I do this according to the definition in the algorithm. So basically, I'm doing exactly this. So it's pretty straightforward. Then this is a state machine, and I use it as a loop. So I have this round counter where I'm counting up the active round. So it's increasing every time we change state. So when we reach 20, we are in the final state. We are done. So we move on to this final step here, where we do the final addition that is defined here. And this works. I wrote some test harness that is using the implementation in Python from, what was it called again? It was this fork. So for some reason, the ChaCha20 is not included in the PyCrypto library, but it's in this PyCrypto for some reason. It works, and it seems to be correct. So I verified it against other implementations as well, so it's kind of useful. And I also tried using a counter and see if that works, and yeah, it seems to work, so that's kind of nice. So I thought today we could see if we can improve this, and if we can make this more, set up some kind of library for it. Because right now I've written this inside of my sort of everything toolbox thing, where I have just a bunch of random stuff, which can be a little bit confusing. So I thought we should set up a new project for this. So yeah, we just need a name. So just 1 second. All right. So names are always fun. So I don't know. If you have any suggestions, just write it in the chat. But I guess, I don't know. We need something. Let's call it we need a name generator. I'm too bad with this. Names are always fun, but we can always rename it later. So let's call it nM crypto. Yeah, let's call it like that. This is the work in progress name. We can always rename it later. So, oh, did that open in this? What? All right. Here we go. Okay, so how do you start a Python project? I'm really bad at that, so I usually copy and paste that from somewhere else. So I guess you can set up setup.py. We can finalize with that, but we don't have to do that right now. Usually you have a directory with sort of the entry point, and inside here you have some init file. I'm not really a Python person, so I just do whatever works. So in this case, I've done something similar before. So the idea is that you can run the module like this. Right. Probably missing something. Guess I need a main as well. Right. right. This is a decent project structure. So let's just reuse that. I wish I knew something about dancing cha-cha salsa. Yeah, it's kind of funny. I'm not really sure why it's called like this, but it's called like this, and it's done by this person, Daniel J. Bernstein, and I think there are even some other. Yeah, it's a lot of dance names here. All right. Okay, so let's set up this structure. So I guess dance of the bits. Yeah, exactly. We can just add some entry point, and then what do you do with this? You add stuff, and then finally you do the parse args, and do something cool. So now we have our entry point. Perfect. Nice. I guess just to compare, we have this, right? That makes sense. Okay, so now we have a very, very basic structure. So my idea is that this can work as sort of a test bench structure, and then inside we have library stuff. And then if from your like if you have a project that wants to use this library, you should just be able to import directly. So like from nm crypto import crypto.ChaCha20 or that's not really how you write it. Yes, it's more like this, something like this. I don't know. So let's create some implementation. Yeah, I should do like this. Right. And if my voice is not loud enough or too loud or something, just write it in the chat and I'll do my best to fix it. Okay, so I don't know, maybe it's too much. Maybe that's good. So I guess one way is to just can start with just copying this implementation. So we have some some baseline. So we can always fix this later. I think there was even some bug here. I did some rewrite. I did a few different alternatives of this with different sort of pros and cons. But yeah, maybe this is better to start from, yeah. I don't know. We can, I think there was some bug here. Right. It's fine. So I wonder what kind of test framework do we want to run this? One way to do it is to have an interface and then implement sort of what's it called? Yeah, basically implementations of an interface. because that way you will have a defined way. And then you can just get implementations or write different implementations for the same interface, which makes sense, I guess. So yeah, where do we want to start? So I'm thinking of both having simulation and also synthesize for different targets, but like having fake targets. So for example, an ECP5 FPGA, but with that doesn't have to exist, and just set up some fake pins just to be able to test the tool chain and see what kind of LUTs and performance we get. I think that would make sense. So I guess I can steal a lot of code from this project, because here I have this sort of dynamic stuff going on, where we are sort of iterating over the applets that we have and creating an argument list for it. I don't know, maybe it's over-designing it. We could do like this. We create an examples. Oh, it's in the wrong directory structure. Right. So in the root, we have the actual Python code, the library in here, and then here we have a example from outside. And here we could do, for example, ChaCha20. And then the idea is to do like from nm crypto import like something like this. I guess that makes sense. And then we can have some main function. Then we can just use some random board. I guess we can use this one because I have it in front of me, more or less. I think I have this one. So what we basically want to do is something similar to a Blinky, just we want to not use Blinky, but rather our own crypto stuff. Yeah. So we need some top level test class. So let's call that I don't know. You can always rename it later. Oh, Jesus. And then elaborate. There we go. Got to import that. Okay, we don't have any signals, so we need some signals. One thing we can do is to do we just request LEDs because they are usually almost all boards have some sort of LEDs, just like a blinky would expect. We can do something like this. Yeah, let's do like this. I guess it's enough to just have one LED. This will be way more simple. We do like this. And then we do so in order to be sure that we're actually using all of the bits in the output stream, I guess we can XOR them all together. So how do we do that? We could do I forgot how reduce works. Basically want to have the XOR operation on all bits. We can do something very simple. And just do something like this. So then we get an expression that is XORing each bit. Yeah. So this way we are sort of forcing the use of every bit in the output stream, but also keeping the logic as basically as small as possible. So we can try and build this, but in order to do that, we need to create the setup file. Oops, what folder? So let's again borrow some code and just call this nmcrypto. Yeah, perfect. Sounds good. Then we should be able to do, just 1 second. Like so. So now we have installed this library that we are working on as an editable library, so that when we change in the source, it will also change in our environment. And --user forces the installation to happen in our home directory and not in a system system environment. So now we should be able to run the example. Okay, it broke. So I guess the reason why it breaks is because the this platform doesn't have an LED source, or resource, but rather an RGB LED resource, which is slightly different. So in order to do this a little bit more generic, we can basically steal all of this. Something that would be nice is to check if we have an LED or an RGB LED, I guess. But yeah, since this is just synthetic, it doesn't matter. We can just, where am I again? We can just use the RGB LED. Do like this, I think. Typo. Okay, it's doing something. It takes some time. That's good. Okay, it's taking quite a while, so you can see what's going on here. Okay, error. We failed. Oh, maybe it's this XOR chain that takes too long time. Okay, let's not do that then. And just do like so. You just look at the least significant bit and don't care about the rest. Hopefully, because it's a crypto function, the tool will figure out that, oh, this bit sort of needs all of the other logic to be, yeah. Maybe we should have a shift register. Yeah, that would perhaps be better. But yeah, it's still failing. Okay, it's because right, okay. So I didn't really think. So this platform runs at 100 megahertz. And the design is simply not that fast. So that's the issue. So what we could do is to change the frequency, because this is still just a synthetic test. Let's see if we can change. Okay. I suppose what we could do is to set up sort of test platforms. So let's call it platforms, and in here we do ECP5 platforms, where we do something similar to a proper platform, but yeah, let's just call it ECP585. Yeah, you can probably not have dashes. Yeah, ECP5 platform. There is a generic one here, right? This is from the nMigen source code. I guess what we can do is to make these more generic. So my idea is that we have like a synthetic platform where we can build test benches. So yeah, we can start here and then we can make it simpler later. Yeah, let's just call it clock. And then we can do like this instead. And then we can create resources, or let's call this data in, and we just butcher this and say whatever. This is a whatever, like this. And then we have like a data out. And we can just set that to the neighboring pin or something. So again, the idea here is not to have something that works in real life, but rather just a test bench setup. All right. Yeah. So I probably forgot parentheses. Here we go. Perfect. Okay. Yeah. So we can probably remove a lot of this. We don't need to program. We can remove this other thing. Yeah, let's just do it like this. Okay, so we can change this to and then crypto.platforms. And just do like this. And do like that. So in order to make this like slightly realistic, we can have a shift register that consumes bits, I guess. I don't know, we can think about this later. But yeah, we can have some some level of realism here. We can, for example, set the counter. Yeah. Okay, so what we're doing here is basically setting up a relationship between the outside world and the core. So yeah, and here in the same way, we are connecting the data out pin with the least significant bit of the output stream. So at least there is something. We can remove that. Yeah, all right. So now, we don't even. We can add arguments and stuff later, and we don't want to program it. Okay, I removed a little bit too much. Let's see here. So I think you need some function here. Let's maybe it's these. I don't remember. Okay, connectors and device. Okay, right. We need a device like so. And we need connectors, which can be empty, I think. Resources, and then connectors. And we don't need this. We need a clock, right? Okay, now it's at least building. So that's good. Okay, that went slightly faster. So we can look at the timing analysis file to see how many resources we are using. In this case, 2,200, which is, I guess, yeah, it's something. And then you should also get a timing report here, where we can see that, okay, we're able to run at 68 megahertz. And this is the logic chain that is causing the longest logic chain that is causing the issue, or like the limitation. So if we would want to run at a faster speed, we can use this information to optimize, basically. So that's cool. That's cool. Now we have something. So I thought, yeah, it would be nice to set up sort of an interface for a generic test platform, because that way we could try and build a core for a different platform. So for example, let's call, yeah, let's think for a while. Yeah, let's say Artix-7. Let's say we want to build for Artix-7. And we should be able to basically copy this and basically rename everything. Thanks for the follow, 3DFX. So what we can do now is we can base our code from something that exists. So we go to nMigen boards and import something. Can I go there? Oh no. Maybe I have the code over here. Hello 3DFX. Yep. So I happen to know that, let's see here. Where is it? Never mind, let's go for an RT instead. Yep. So I think this is an Artix, right? So I don't know these chip names in my head. I need to use Google. But yeah, that's an Artix. Okay, perfect. So let's create a test bench based on this chip, because here we have some pins and we don't need to look up too much. It should be basically just copy and paste. I guess we can just copy like this. And instead of RT, let's call it Artix-7 platform. Yes, that makes sense. And then, yeah, these are of course specific for this specific chip. And again, let's just call the clock signal clock, and remove that. Now we just need to copy some pins from over here. So, all right. It really doesn't matter because all of this is fake anyway. So, right. So here we're faking the clock to be, did we say 16 megahertz? And of course we can change this from the test bench. That's the whole idea with this. So later on we will have sort of enumerable configurations so that we can basically generate a test bench and get a timing report for basically any chip that the tool chain supports. That's at least my idea here. Should be okay to do. So I'm just using some random pin. I have no idea if these pins are fast or slow or whatever. Who knows? Maybe they are on different IO banks. I don't know. It might matter, of course, because you can do better floor planning if you're like in the same quadrant of the chip or section, I suppose. So yeah, I guess later on we can look at that. But right now I just want something. So the idea now is that we go to, let's see here, here in our example. And instead of the ECP5 platform, I guess we should be able to do like that. And then in the init file here, we need to do some stuff. So I'm, again, not super good at Python, but I'm good at copy and pasting stuff. So how do you do this in a sane way? So what I want to do now is to basically get the get access to all of the platforms by doing like this. But I guess we can do that later. So for now, I can just do like this, like so. And we can do this. And then now we can do another test build. And it failed. Why? Line 6. Right. We don't need this. Here we go. Cannot find Vivado. Why not? That's weird, because I was building something just a few days ago. Let's try again. Just 1 second. Could it be that Lattice is doing something other with the whole environment so that this doesn't work? Okay, I guess a part of this stream will now be how to set up your toolchain correctly. Crap. because I have this this and this. Okay, so let's see if I can get this working. I guess one way to do it is to run the nMigen boards, and then instead of this one, let's okay. Let's yeah, let's try to build this one then. Okay, so what does it say here? Couldn't find Vivado as specified. Okay, it's actually true. So it looks like it's doing some double. Oh, I see what it's doing. So I guess I should do like this instead. Yeah, okay, this seems to work much better. That's interesting. Okay, I'll fix my environment. Okay, this looks better. So yeah, we can kill this. And also this. So back to what we were doing. So we set up this fake board with just random pins, and very, very simple. And we are using it here. And for some reason it does not work. Specified part could not be found. So I guess I made some mistake somewhere. Let's see in the... Yeah, I wonder which file could that be. Let's try again. Yeah, okay, so top.log is the main log file. And okay, something failed here. Specified part. So it's the same thing, yeah. I wish there was more information. I suppose it's this that it doesn't find. Did I mix up something here, perhaps? This one, yeah. Oh, so my mistake was that I had some old stuff from the ECP5 example. But yeah, okay, whatever. Now we are back in business, I hope. Yeah, let's see how it goes. It's working. It's using some CPU, but mostly just one thread, sadly. I have no idea what it's actually doing here. It's doing a lot. Place and route and stuff, I guess. So I guess these are our resources. Okay. Okay, so this seems to be the timing report, I suppose. Right, so this is our input frequency that we specified to be 16 megahertz, just to be like 100% sure that it will synthesize. Oh no, it failed. So why did it fail? Did I mess something up? Okay. Unspecified IO standard. Oh no, okay. So I need to do some more specific instantiation of our, or definition of our pins. So I was hoping that I would be able to just steal stuff from nMigen boards.rt import RT platform. So what did I mess up here? We have this clock and reset pin. Those are important. So now they are 100% copy and pasted. And the clock is set to this one. And then for some IO pins, yeah, we can use the UART pins. That's safe. So it's gonna have to be... Okay, so the problem was that I didn't have an IO standard here. So that's the problem. So yeah, let's just do that. How do you do that again? I think you just add it in the end, right? Like so. So now we have our data in and data out. And let's use the UART pins because why not? A9 and D10. Perfect. Okay, let's do this again. Oh no, it failed. Oh, because I didn't rename it. Let's try again. So I guess it Vivado takes yeah, a few minutes to run. It is how it is, I suppose. So yeah. I think this will be kind of interesting. Like once we have a few more platforms, I also have a Cyclone V toolchain installed that should work. We can try it. Let's see, where did I put that? So I made a board definition for the God damn it, I already forgot the name of the board. Chameleon 96, there we go. So we can just try to build the example project the Blinky basically, just to test that the toolchain is still working. So here we have a Quartus, which you need for Altera FPGAs. The other one is for Xilinx. And these toolchains are not small. They take up basically like cyberpunk size, or modern game, almost 100 gigabytes or something. I don't know. So they are big. So this will work. I mean, it will be working for a while. So yeah. Oh, it finished, and it didn't fail. So that's really good. So I want to see our final timing, the final timing report. See if I have that somewhere. Timing report, where could that be? Maybe this one? I'm just gonna search for megahertz. Oh, here we go. This looks like the timing report. Okay, so the top.tim, that makes sense. Oh, wait a minute, isn't this for the ECP5? It is. Why do I still have that? Okay, CPU speed. That's my comments. So I don't really understand. Maybe I'm missing something. Because I want to see like what is the timing report for our project. What is the fastest clock I can use? Because here it basically says, yes, you're able to use the clock. It will be fine, but is it this? Guess we need to read the documentation. I have no idea. But let's try to understand it together. And if anyone in the chat knows what this means and how to read it, just please write in the chat and let me know. Because this is actually, I haven't done anything remotely serious in the Xilinx tools. I basically just built something and tested it. And from this report, there's like so much information here. I have no idea really what to look for. But we can see something about here, right? This is how many XORs I have and adders, I suppose. And there was some information about the LUTs. Yeah, right, here. The cells I'm using. Would be nice with sort of a shorthand of what this actually means. FDRE, maybe some flip-flop or something, who knows. These are sort of self-explanatory. Carry and buffer thing. I mean, I can sort of guess what this is, but this, I have no idea what it is. Okay. This looks like our board definition is not really correct. The IO type, that is, nMigen generates these files, I think. XDC. Do I have it here? Right, so here it's actually complaining that IO type shouldn't be there. But it's not. That's... Oh, it's because I am actually asking for it. Here we have the IO types, right? but here we don't. So why is it complaining? Oh, it was the backup log. Okay, confusing. Never mind. Don't look at old logs. That's a bad mistake to do, I guess. Okay, so let's look at the actual log. I still don't really see the timing report. I don't know. Should be here somewhere. Like, yeah, sure, the timing constraints are met, which means it is fast enough, which is cool, but so is this it? So I guess if we do some math, FD are flip-flops. Okay, thank you. Right, so no, right, I can never do proper math on stream. Like, how do I convert nanoseconds to megahertz? Is it 1000 divided by it? No. Ah, God damn it. I never find a good way to check the maximum clock when the clock is smaller than the maximum. The only way I found is force a bigger clock in a way that Vivado will show the worst path. Okay, that's interesting. So, okay, so you don't really get informed about, okay, your design can run at 120 megahertz. It's awesome. But rather, yes, it passed, and you should be happy. That's interesting. So if I boost this clock to, let's say, 100 megahertz, then let's just clean up here a little bit. And then we build it again. And then 5 minutes later or so, we have a new timing report to look at, and maybe it will not be this fast. Who knows? So we got like 65 megahertz on the ECP5 at speed grade 8, I think. And this FPGA should be slightly faster, or perhaps even a lot faster. I don't know. I think it's supposed to be able to run a bit faster at least. So now I just boosted it to 100 megahertz, and yeah, let's let it finish and see what it says. No, because usually when you read papers about FPGA stuff, they include like performance benchmarks and so on, which are, I mean, they usually report it for Xilinx as well, which is kind of interesting. Like I have this paper here about ChaCha20 and Poly 1305, which is an interesting read. But they have this example implementation for a Vertex 7, so really beefy one. And here they report that, oh, they get 161.02 megahertz. So have they like brute forced them to that number? I don't know. ISE is far better in this case. Okay, because ISE always shows by default the worst path. Unfortunately, ISE does not support. You're right. Like Spartan 6 and so on works, right? But Series 7 is too new. Okay. I think it's getting closer. So let's see here. Did it fail? Or because I'm not used to look at this at all, so I don't really see, like, when you spot a GCC error, you see it immediately, and you know, like, oh, okay, here's a negative time. So I suppose that means that it cannot run this fast. So we should probably get an error here somewhere. Let's see here. Yes, series 3 and 6. Few devices from 7, such as Artix-7, Kintex-7. Okay. Okay, so it can... interesting. I thought it was like a hard limit that, oh, series 7, no go. But that's interesting. But I suppose ISE, isn't that sort of dead? What's it called? Like not maintained anymore. I don't know. But it seems like Vivado is what people are using. But anyway, maybe you can help me understand this timing summary. Like, if we look for... Did we like get a bit stream? Yes, we got a bit stream. Glitch cat. Is that the emoji or emoticon or thing? I missed it. Crap. Because I have the IRC here. Anyway. So I got my bit stream here. Oh, there's a usage thing. Should we look at that perhaps? Oh wow, that's a lot of information. So, ooh. The last IC version is something like 10 years old. Oh wow, okay, I see. Okay. So, okay, maybe that's a license thing that I am not allowed to use more processors. Okay. Command line options, blah blah blah. Ooh, so much data. Okay, this starts to get interesting. Primitives, right. Slice logic. Then, okay, but what about the timing report? Crap. Okay, it doesn't really say anything. Yeah, I mean, as you can guess, I am a total noob at this. I've played around with the open source tools for ECP5 mostly, and they are super nice to use and very easy to understand. Yeah, this is basically a mountain of information, and I don't... Yeah, maybe we can just accept that, yeah, okay, we are able to synthesize some stuff for Xilinx, and that's cool, and move on. But here's actually some information. I mean, this... Okay, timing constraints are not met. Maybe I forgot to clean before building again. Maybe that's why I have a bit stream. Yeah, that's probably it. So I suppose this means that, or this means that we are this much over the desired frequency, which is a pain to parse. Like, I guess this is really useful for people who know what they're doing, but for me, I don't know. Okay. Okay, let's move on. Okay, so let us build Cyclone V variant as well. Then we have sort of a... Oops. We have a few platforms that we can test on. So like so. And similar to this, we can use the Chameleon 96 and base our design, our fake platform on that. So let's just do like this, clean it up a little bit. All right, I didn't have a clock input on this board. It's using the internal clock, which is a little bit of a pain because it will infer some extra resources. So I'm just gonna fake a clock. So let's do a mashup here. So we have the default clock. Let's do like this. Then so here we don't need to use an IO standard because it will be I think 3.3 CMOS, LV-CMOS by default. And I just need some pins, so we can just use some random pins here. All right, a clock should be a clock input, I suppose, but we can try it, see if it works. And then we need the data in and data out. We can just use these pins. I don't know if they are directional, but I know that some pins are directional on that chip. You can just try it with something simple. It's doing something. That's a good sign. I completely forgot, but maybe the font size is too small. Anyway, if anything is wrong, just complain and I'll try to fix it. I have no idea what's going on, but it's doing something. It's using one core at 100%. Okay. Guess it's a license thing as well. Or perhaps it's the algorithm, who knows. It's still working. Whatever it's doing. Yeah, this is the generated Verilog. So 2000 lines of Verilog. Most of it is just plumbing, I guess. Like all of this stuff here. Here we have the actual algorithm. Yeah, I don't know how long this will take, but yeah, Cyclone 5 is a little bit bigger FPGA, so I suppose it can take a few minutes. Oh, I forgot which frequency it is at. 16 megahertz. Okay, that's good. So it would have been kind of sad if it failed for timing reasons, and we wait like 5 minutes in vain. I hope it will finish within 5 minutes. I don't know. Anyway, we can let it work in the background. What extension for Visual Studio Code do you suggest for starting with FPGA? So in this case, I'm using nMigen, which is 100% Python based. So just any Python plugin that you're already using for normal Python stuff. And then once you import nMigen like this, you can just start coding. Oh, something is happening. So this is the RTL. It's Python, so it's really convenient and kind of lightweight because you can use basically Vim or whatever. Like you don't need a huge IDE to do this. Okay, stuff is happening. It looks interesting. So I guess here it's saying that, yes, the clock is running at 16 megahertz. And so here something is happening. Worst case setup slack is 60. Is that nanoseconds perhaps? I would guess so. That sounds really close to 16 megahertz. Again, here's... okay. I'm not really sure how to read this either. Okay, here it's finished. Yeah, I've never really looked at this report from the Altera tools. I have no idea really what to look for. I'm just happy I got a bit stream basically, because I think I did right. So this looks a little bit different. What is the bitstream even called? RBF. So if I have an RBF file, it's all good. Yep, and I do. Okay, perfect. And the RPT files. Okay, there's the report, and there's the summary. Okay. Interesting. Okay, so maybe this is the timing analyzer summary. Okay. I have no idea how to read this, how to interpret this into actual numbers. Like, here, oh, look at this. Fmax 300 megahertz. That seems like way too high. Or Could that actually be how fast the design is on Cyclone 5? Because this is a pretty, like, it's a pretty beefy one. 300 megahertz seems like very high. Like, the other ones were like 60. So I don't know, 300. That's, yeah, I don't know. So let's call this 16M, and then just for the fun of it, we can just boost the clock here to, yeah, let's say 150 megahertz and see if that builds. We can let it build in the background, and then we can code and improve stuff while that is working. Okay, so there's only one way to know. Test it with 300 megahertz. Yeah, you're right. I'm just feeling that if I actually run it at 300, who knows? Maybe it will work. Because now I'm running it at 150. So if this works, yeah, I guess we can try 300 as well. But yeah, while this is running, we can continue. So I'm just gonna yeah, I can just move this here, and let's think a little bit, and then right. Yeah, what should we do now? So should we perhaps add unit tests? That's, I mean, it's kind of boring, but it's also a little bit interesting because then we are able to refactor and test this properly. So again, what I said in the beginning was to try to set up a framework for with like a nice interface, so that we have like a generic crypto block, and then we can have a test bench for that, so that we can try out different implementations and optimize it and so on. So yeah, I don't know. I'm trying to think of a good way to move forward. Software design is always like, yeah, sure, if you get it right the first time, you're probably a wizard. I don't know. I usually have to iterate a few times before getting it in a nice way. So maybe we should just prototype and see where we end up. So how do we want to structure this? Like, we can always just do it the simple way and do it like this, and use the unit test framework from Python, and basically use that. Then we can implement some generic test stuff, I suppose. So in this case, we want to run crypto.ChaCha20, and then here we will add unit tests. Oh, this failed. Why? All right, I tried to program it, right? And since it's not connected, it wouldn't do that. That makes sense. Okay, so where do we go here? Here. There is a way to calculate the Fmax in Vivado. Okay, that's super helpful. Thank you. Right. So the WNS. Worst negative slack. Okay. So wait a minute, does this mean that if your design fails, so let's say you're trying to build it for 1 gigahertz and it will say, oh, it's too fast. You need to slow down with this much. That will give you the Fmax. So I think it is very confusing. Yeah, I agree. But I think, okay, I was a little bit, oh, it actually finished. So just a sidetrack. Here's the Cyclone V. And it looks like it actually finished. Because we have the RBF file. Very cool. And here we have the clock slack thing. Does it still say 300 megahertz somewhere? Oh, it's so green, I can't really see anything. I need to open it in a different editor. Here we have the summary. And here we have the report. Oh, okay. So 312 megahertz. Oh, that's insane. That's... holy crap. Okay, so it seems that the design is quite fast on the Cyclone V. Or I'm basically missing something. So let's call this the 150 megahertz, and then let's build for Vivado again. Did we have the example here? We do this one, and then let's change it to 100 megahertz again, because that failed, right? And we build with an empty build directory, yep. So here we go. Perfect. And if I don't misremember, it should be like -1 or something nanoseconds. So I guess it's 100 megahertz minus, so basically 10 nanoseconds plus 1 nanosecond, so like 11 nanoseconds, I think. 1 divided by t minus WNS. So t in my case is the 100 megahertz clock, right? That would make sense. Yeah, anyway, we're learning. Hopefully, yeah, you can come. Let's see here. I think it's almost done. Yeah, I mean, the reason why I do the streams is so that I can make mistakes and people can correct me, and hopefully someone else can also learn something by watching me fail and learn. That's at least why I'm doing this, so. Yeah. Okay. It's still working. Okay. Okay, so now we have a new report, minus 1.776. So our large T is this one, right? 10 nanoseconds. So 1 divided by 10 minus 1.776, so basically plus. And then we get 84 megahertz, and that seems way more reasonable, right? That could actually work. So if I try to resynthesize this, let's just call this build Xilinx 100 megahertz, and then we can change this to be 80 megahertz, because that should be fine, right? So if the absolute max is like 84.9, then 80 should be okay. So let's build that again, and let it work. Yeah. Okay, I hope it's finishing up soon. Watching Vivado work, I can think of more fun things to watch. Right. I'm not really working with anything of this, it's just a hobby of mine, so I'm learning while doing, and a lot of these things are confusing to me, and probably also confusing to other people who are starting out. But yeah, hopefully we can learn together. Okay, creating bitmap sounds like the final step. Okay, so it actually managed to produce a bit stream this time. So let's have a look. Yep, and this time it worked. And we get this WNS of 0.256. So let's do the opposite. So this time we want to remove 0.256, and we, all right. Right, it's not 10 this time. This time it's 80, right, 12.5. Yeah. Okay, so to do a recap. Previously, we built with 100 megahertz, 10 nanoseconds, and we got a negative slack of 1.776 nanoseconds. Putting that into this equation, we get almost 85 megahertz. This time we build it with 80 megahertz as a target, and we get a WNS slack of 0.256. And putting the 12.5 into the equation, like so, and then using this WNS as a negative, yeah, like boosting the 12.5 to make it a little bit faster, we get only 81.6. So here we can see that if you have a timing budget, like this timing budget is not the maximum budget. So just like the internet person said here, you have to go beyond the maximum frequency. So I guess, yeah, we've verified that, yeah, this is basically how you have to do it on Xilinx. So there you have it. Try to build with a too fast clock and then do the math to figure out the maximum frequency. So now we know how that works for Xilinx. Perfect. And for the Cyclone V, I'm honestly really impressed, because if this is actually true, that we can run it at 300 megahertz, that's nuts. This was Xilinx at 80 megahertz. Yeah, that's super cool. So now let's do the test with the Cyclone V platform and put in 300, well, not 3000. That would be a little bit too much. But yeah, now we have a Cyclone V with a 300 megahertz target. And we don't have a build directory, so let's build it and see what happens. And this one was really slow, so let's do something else while it's working. Why is this? I wonder, did I have a change here? Okay, just a few white spaces. Okay, so going back to the unit tests, what would be a nice Pythonic way to do this? So, oh, okay, here we have it. Maybe it's possible to compare the amount of logic between Xilinx and Altera in order to ensure that the circuit is really complete. Maybe there's something missing in the Altera version. Yeah, perhaps. And also, since this, like, this is cheating a lot, we cannot really trust these values either, because here basically I'm just setting 1 bit of the input matrix. So this is the initial matrix, and this contains 1 single bit from the outside world. But at least it should, so for example, this and this will be completely ignored. So it will just be zeros, which, I mean, yeah, we should probably improve that, make some shift register or something, just something so that you have, so that you're able to run the core properly. But yeah, let's have a look. So for example, Xilinx 80 megahertz, and look at the utilization, I guess, placing perhaps. Here we see how many LUTs we're using. Okay, perfect. So we have used 1600 slice LUTs and 500-ish registers. Okay. And if we compare this with the Altera, was it, yeah, this one at 150 megahertz. Was it the report? I think so. No. That was the timing summary. Maybe this one. Oh, this seems really low, yeah. 23 registers. That's nothing. I guess they call LUTs ALMs. Yeah, I've seen that as well somewhere. Oy. Okay. Oh. This sounds like the generated Verilog basically throughout the whole file. Or, I mean, we can have a look at this. line, say 631. Okay, it's part of the state machine, but that should be used. Yeah, okay, I'm starting to worry that this is actually very much incomplete. Because also 300 megahertz sounds like way too fast. Yeah, this seems really low. 25. I would expect like a few hundreds, maybe 1,000 something. It could be that the clock is not working or something. No, look at this. Here we have a few hundred LEs at least. We know that we have 23 registers. That can work. Yeah, exactly. But yeah, let's see if we can see something. No, this seems... I don't know what loot depth is, but all of this seems like extremely low. Weird. Because essentially what I'm doing here, if we just look at it, is basically we're controlling the least significant bit of the hashing algorithm, or a crypto algorithm. We have a key of zeros and a nonce of zeros, and we're outputting the LSB of the stream. So this one can only be 0 or 1, and it's depending on only 0 or 1. So I guess if the tool is smart enough, it can essentially simulate the whole circuit and try it out with a 0 here and a 1 here and see what the output becomes. So yeah, I suppose maybe the tool was too smart, which means that we need a shift register to fool it. But this can help us to create a test bench that makes sense. So let's prototype using the ECP5 platform. So what do we need? We need key and yeah, how do we want this? I honestly don't really know what is most efficient to do. Like if you have a really long shift register, is that sort of expensive to implement? Like for example, if you do 512-bit long shift register, and then sort of you do key basically we have a 512-bit long shift register here, which we are feeding with 1 bit that comes from the data in. Because there are so many bits here, I'm not really sure what would be the cheapest way. Because the thing I want to sort of avoid is to have too much logic outside of the core, because I want to sort of benchmark the core. I know for the ECP5 tools, next PNR, ECP5, you have this one, out of context, which will disable IO buffer insertion and global promoting and routing for building pre-routed blocks, experimental. So essentially, if you write a core and just don't want the tool to prune off unused pins and so on, this is what you can use. But at the same time, it would be nice to have like a test bench that actually works. Like for example, let's say you use UART and feed a key from the outside world, and you feed a nonce and a counter and a data stream that you want to encrypt, and then you sort of perform the, you run the whole block on that, and then you output the result using UART as well. That would be a sort of a neat test. And I wrote something like that, but it was horribly expensive to do. I probably did something really, really stupid. Again, I'm just learning while doing. So yeah, here's a bunch of commented out code, but essentially I had this long register that I'm sort of picking out which byte to print. And that seems to generate like a huge MUX tree, which is expensive, I suppose. So yeah, let's not do that and try to do something smarter. So yeah, so here we have a key, which will be a bit register, 1 bit wide. And so here we are. So 15 bits, right? So we will append 1 bit in the beginning. So for example, in the beginning it's all zeros, and then we shift in a 1, and then perhaps 0, and it will all shift in I'm really not pedagogic. in this direction. So when you use the cut operator, the first element will be the least significant bit. So if this data in is here. Oh god, this gets really annoying. So if there is a 1 on the data line, yeah, it will become like this. Oh. So I hope that makes sense. So there we go. And then at the same time, we can do something similar with nonce. And a nonce is, let's just write it like this instead. A nonce is, makes sense, yeah. But it is sort of confusing because in Verilog, it's the opposite. Like when you write this operator, and you do like so. So it's the opposite. This is the MSB part, if I remember correctly. So for example, like if you do a 1 and a 0, what is this in OB notation? Is it this one or is it this one? It's kind of confusing. So if I remember correctly, it's actually this one. So this looks more like if you write it down, like this, if you have this bit stream, it becomes this. But with the cat notation, it is like this instead. So it's flipped around. Anyway, a small sidetrack, and that might like get confusing in the head sometimes, like what is the order of the bits? Yeah, okay. So, so let's do the nonce. The nonce was 3 times 8. Perfect. There we go. And since we don't really care about anything of this, we just shift data in. Yeah, maybe we should have like separate signals for like key nonce counter. So let's add that to the generic platform. So let's call that key in and nonce in and counter in. I think that makes sense. Then we need some pins. Yeah, let's yeah, we need some new pins. Maybe I have this open. Yeah, there we go. So I'm just gonna take some random pins from here. Yeah, should be good enough. And let's go back to our example here. Okay, so you can write this in a nicer way, but let's just start with a very simple way. And counter in. Okay, so now we have actual bits that all right. Yeah. Okay. So we have an actual key, an actual nonce, actual counter, and actual data. We don't use the data yet, because right now we're only creating a bit stream, like a key stream. So let's save that for later. Save that for later. And then here, the counter, we can do like that. Right, and these can actually be in the non-synchronous, what's it called again? Comp logic. Like we always connect the counter register essentially as comp logic. And actually, this is not right. There we go. So ChaCha20 works with 32-bit integers or unsigned integers. And internally, we're using it in a big endian mode. And that caused some trouble before when I was simulating it. But that's all fixed now. So anyway, now we have a proper key nonce counter, and the engine knows about the counter. Perfect. And yeah, now comes the sort of horrible part, because I'm not really sure what the best way is to handle wide buses, essentially. So the way I did it was to use Python arrays, because I don't need to index inside of them. I just need a way to have multiple multiple words, essentially. So now we have these sort of wide signals, and now we need to sort of wordify them. So, oops, what happened there? Right. So let's do that. So we want to set ChaCha20.I. Oh, maybe it was that simple. I forgot to enable the core. Now I feel like super stupid. But anyway, this is a good exercise. We should enable it over here. Here we go. Yeah, that was stupid. Okay, so the counter is done. The key is at ChaCha20.I key, and we operate on I. Yeah, we can do it the other way around, like so. And then we do key (64) no 32 times I to 32 times I plus 32. Does this make sense? So we're setting each 32-bit signal in the key, because that's what we have, right? We have this shape of a signal, a 32-bit signal, and we have 8 of them. Right. And it shouldn't be, and 32 is for the 32 bits, right? Yeah, and then the bit order might be wrong, I don't know, doesn't matter. We just want to exercise and connect all of the signals here, so that should be fine. So I think this is okay. So let's do the same thing for the nonce. And what more? Key, nonce, counter. And then enable. I'm going to enable it here. Okay, so let's build it for the ECP5. Oh, we need an output as well. We need, so we can have O data. And this one should be 16 times 32, because the matrix is 4 by 4 and we have 32-bit words. So this should be fine. Let's think a little bit. So the idea is to like shift out a bit at a time. This time, maybe we don't have to care about that, and we only use the LSB. Yeah, let's do that. So ChaCha20.o stream least significant bit. We do data out equals that. So in order to derive what the least significant bit is of the crypto, we need to perform all of the cryptography and like exercise all of the logic, because nobody can know if this is a 0 or 1 based on like you cannot do that statically. At least I don't think so. I mean, I guess you can, but it would be super hard. Okay, what we do now? We have this. Yep. Yep. Let's no crap. So what did I mess up? 39. There we go. Did I forget that somewhere else? No. Okay. Looks good. Okay, it's done. Still complains about unprocessed init attribute for some reason. Maybe it's related to the output not being used properly. Let's have a look. Let's see if I can just find what the signal is. So this comes from line number 19. Let's see what that is. Yeah, it is the output stream. So I suppose what we can do is like this. And then like that. Oh, so we're iterating over the 32 or 16 32-bit words of the output stream, and we are setting it to the let's call it stream. Keep it consistent. So this is the key stream, and we're using the same logic as before. So we have a very long single bit signal, so like it's one signal with many bits. And then data out, the question is what we want to do now. I mean, we can do like this, but this means that we're also just disregarding all of the other bits. We're only looking at the least significant one. So I don't know, maybe this will shut up the warnings. Oh, nope. We just got a bunch of others. Oh, this is no good. Right, I should flip these. So the mistake I made was that I was trying to set the output with my shift register, which is the other way around. So here I'm setting the shift register with the value that comes from here, which makes way more sense. But now, okay, it's better, but still worse. I don't know, something terribly, I don't know. Why? How could it be so fast? That feels like something is wrong. It's super fast. Yeah, there are no LUTs. So, I don't know. Data out is my pin, which I have here, right? Data out. Yeah. Let's do it like that. Stream. I don't really understand what's going on here. Well, I'm just gonna be lazy and do like this. Hope that will be good enough. Yeah, takes more time now. But yeah, it's complaining about the output bits, that we're not using all of them. But I wonder how much extra logic this costs. I don't know. It's always kind of hard doing synthetic profiling things when you don't have a reasonable logic core. Oh shit, look at this. It's using tons of logic. Like this is using like 1000 extra slices just because I'm using that shift register stuff. But the timing at least seems to be okay. Yeah. I don't know really what is a good way to... I mean, the problem is that we have so wide signals. We have so many bits that go into our box. And if we do, like, it doesn't really matter what we do with those signals. Like, we need to connect them somewhere. And yeah, I mean, this is a lot of bits. So we have 16 times 32 times 8, 4096 bits. No, that's not correct. It's 512 bits. But even if we would like connect all of these to input pins on the FPGA, like we would need the key plus the nonce plus the counter. Or the counter could be internal for sure. But yeah, that's still this much for inputs. And then this much for outputs. Times 32 bits. That's 864 pins if we would connect these to like actual pins on the FPGA. So it's kind of insane. Doesn't make sense to do. Yeah, I don't know. Yeah, this turned out to be a little bit harder than I thought to like make a test bench that makes sense. Like maybe one way to do it is to have sort of a baseline. Like you have a crypto thing that doesn't do anything. It just passes the signals through. And use that as a baseline. Like if that costs, let's say 1500 lutz, then you can subtract that. I don't know, it doesn't really make sense. In any way, I don't know, maybe this is just crap. Maybe we should do something proper instead. Maybe RAM is the way to go, and muxes, so that you store the bits into RAM and then you load the registers from the RAM. That way you don't get these sort of big registers, like this huge register array. I don't know. This was sort of a tangent, but still kind of interesting. I'm seeing it's already 9 o'clock. I think I've been streaming now for 2 hours, right? Yeah. I don't know. Maybe it's time to move on to the next step. So let's see if we can simplify this. So I'm just gonna copy this and make it simple again and see if we can get it to work. So let's just make it simple. So let's keep the counter, keep the data out, and because what I was missing last time was this enable, so that the whole core was basically sleeping. So that wasn't that strange that it got pruned. So it's almost like interesting that the other tools didn't prune it. So, well, now we know. Now we can kill this. So just double check. We're setting the counter, we are setting the enable, and we are reading from the output stream. Yep, this should be it. So let's build and see what happens. yeah, this looks saner. 2600 slices. And we're not doing anything like stupid here. And we can see here 68 megahertz. Yeah, that seems way more reasonable. Yeah, because that's speed grade 8. So just to, let's call this ECP5 and just speed grade 8. And let's just build the same thing again, but with the speed grade 6, which is a slower speed grade. It failed. Oh, okay, because I am using this one. Yeah, I should, 1 second. We should be using this one, I guess. Or actually there's 380 something. This is a good package because I think all of the different variants are available in it. So you get the different speed grades and you get yeah, different feature sets. And the 45 variant, if I remember correctly, you can get this one in basically any package and speed. So it makes more sense to use that. Now we just need to map up the resources a little bit. So the clock G2. Yeah, let's just use some random pins. Okay, and it's done. Yeah, 2600, and oof, this was not fast. 43. And just to make a double check with the 8th variant, I'm just gonna run it again. Okay, perfect. I still think we learned quite a lot today. We set up this new Python framework. I will be cleaning this up and putting it up on GitHub and so on. And hopefully in a while we will be able to grow the library with more cores and also interface the cores with actual in Lattice would be fun. That could be a nice stream to sort of go through the whole process of yeah, doing that. So now we have the same LUTs 2611 and 50. Wait a minute, this doesn't make sense. Could it be that I should boost the clock so that it's forcing the tool to work harder? Let's think one more time. So I have speed 8. I'm using the basic LFE5U, not UM or 5G. And I have the clock set to something low, but if I set it to, say, 60, will this force next PNR to route better? I think it might, but yeah. Maybe we should do the Xilinx approach. Target a high clock and then see how much we went over. Yeah, because now we got a fail at 56, 57. Oh, right, wait a minute here. If I remember correctly, the 5G parts are not just running at speed grade 8, but they are also running at 1.2 volt instead of 1.1 volt, and that gives you quite a significant speed boost as well. So I think that might be what we're seeing here, to be honest. So if we compare here, yeah, right, because here we get 43, and then here we get 57, which is faster, and then with the 5G we got even faster. So if we do like this, is it EM5G? Yeah, this one should be even faster. So this is actually kind of interesting. So again, I should have like a matrix of, or an array of all the permutations of devices, and then you can sort of run this with an automated script to determine the fastest or whatever performance, get some nice performance values. So again, this is now with the UM5G variant. We can see here that we get 67 megahertz, so that is a quite significant boost. So that's kind of cool. What did we have? 59. Yeah. 67. Cool. So there's also the UM, which I don't know that much about. Yeah, I think it has high-speed transceivers, but only 2.5 gigahertz. I don't remember if this runs at 1.1 or 1.2, but this one definitely runs at 1.1 volt, and this one at 1.2 volt. So it might be interesting for benchmark reasons to include all the different permutations. So let's just keep some notes. 6, 7, 8, and 8. Yeah. Yeah, something like this. So when I write this code, I can remember this. Yeah, let's put that back. All right. Okay, so this stream has been mostly plumbing and getting stuff sort of working, and less doing what I actually wanted to do, which is to make the pipelined version of ChaCha20. But at least we have this sort of yeah, structure up so that we can go beyond from here. I don't know. Maybe I should clean this up a little bit. Yeah. But yeah, this was really helpful. I didn't know about this, but now I do, so that's kind of cool. Yeah, actually, we could do a test run on the Cyclone 5 before we move on. So let's do that. Where do we have that again? Here we go. So Cyclone 5, clean up and build. Oops. What did I break? All right, I need to fix the signals. So let's go and fix that. We need these things, because these signals make sense to have even in the future, I think. At least you get like, yeah, it makes sense to have. But for now I can just comment them out, I think. Right. I use counter in and data out. Okay. Cool. Oh, I'm in the wrong file. So let's just rename it. Here we go. Okay, so this will again, I guess, take 1 hour. No, but like a few minutes. So let's. I'm gonna take a short break, so I can just make this full screen, and I'll be back in a few minutes. All right. All right, so let's see how this went. Looks like we have some negative slack, which I suppose means that our clock of 300 megahertz was slightly too fast. But that's fine. Let's just read the output and try to learn something from it. Yeah, this time we got 539 registers and probably a few ALMs. Okay, not available because we went overboard. Interesting. Let's look at this. So it figured out how many registers, but it could not figure out the utilization. So I suppose this happened because it failed timing. But here we have some ALUT, whatever that means. Arithmetic LUT, perhaps, I don't know. And ALMs. Ah, okay, so it's an estimation, and then after it does the place on route, it knows for sure how many were needed. Okay. I have no idea what this really means, but it sounds interesting. I suppose it's some optimization help. Yeah, this is the output, the stream output, I think. Yeah. So in order to get like a proper value, we need to do something with all of these signals, I think. This is really interesting. So we have like a depth of 16 LUTs. I guess that means you have a clocked signal, like a register that goes through 16 number of LUTs deep until it reaches the next flip-flop. So I guess if we want to make it faster, we want to lower this so that the chain is shorter. Okay, let's see if we can find... No, okay, so we just... okay, but we got some lag, right? No? Some of this... Was it... So I'm still looking for like the timing report. Okay, here. Oh, that sounds super bad. But I don't know what the unit is. Maybe it's picoseconds. And then it would be -6. You know, let's do this again, but with a more sane clock. Let's do 16 megahertz because that will probably work. I would be surprised if we fail timing at 16 megahertz at least. I would guess that we're gonna get something around. It's really hard to say. Really hard to say because the Cyclone V is much bigger. I think it's like 100k LUT, yeah, 110k LEs, whatever that means, but it's a pretty beefy one. So yeah, it's a big one, but I don't know how fast it is. No idea. And from other benchmarks, it seems that it might be a little bit slower than the Xilinx Series 7 Artix. So for example, if we look at some other implementations like this, right, here's another ChaCha stream Cipher implementation. And here we can see that on the Cyclone V, now that this is the GX, and we're using the SE, right? SE. So here they get 60 megahertz of Fmax, but with the same RTL, they get 100 megahertz on a Artix-7. So that's like a huge difference. Anyway, let's see what we get. Oh, it's done. Okay, that went surprisingly fast. So Okay. So here we got actually a frequency, 43.7 megahertz. So this is basically in the same ballpark as the ECP5 speed grade 6, if I don't remember incorrectly. Yeah, here we have 43 megahertz, and here we have 43.7. So essentially the same. So that's interesting. And if we look at the oh, wait a minute. I'm just gonna rerun that test. So let's call this like this, and then do another run on the ECP5. And set the speed grade to 6 and the device to the 1.1 volt. Yeah, this was pretty fast to run, so should be done pretty soon. Yeah, any second. Yeah, this is the 2611, right? So I think we should get the same speed as before. Yeah, 43.5. So this is perfect. So now we have a couple of ballpark values that we can probably trust, at least a little bit. So yeah. So if we just compare it with this code, then we see that, okay, fine, this code is slower, but I haven't even, started optimizing it. It's what it is. It's a naive approach. Okay. I think I will wrap it up now and do some cleanup and set up a repository and commit the code and so on. And then during the next stream, I can improve stuff and add more algorithms and so on. So yeah, today was unfortunately not that much nMigen specific RTL coding, but more of a project setup stream. But anyway, now we have this, and we can build on top of that and expand it. So thanks everyone for joining and writing in the chat and so on. It's really nice to have the interaction. So thanks, and see you next time. All right.